Okay, so let's talk about thermal resistances. I said we'd talk about this next. Again, this is a bit of a review, but there's some slight differences that we'll talk about in this course that I think are important. So we've gone through this exercise. We just decided that this is the heat flow equation. Our resistance is in the denominator, so you flip it and you get ln R out over Rn, 2 pi Lk, Th minus Tc, right? That's our heat transfer rate for this problem. So the concept of thermal resistance is really analogous or derived from the electrical resistance concept. If you have some situation where, let's say you have voltage, right, VH, and you have another voltage that's lower, we'll call that VL, and you have some resistor that's between those two voltages. As long as you have a voltage present, you're going to have some current, right, some current that's moving. So we'll call that current I. The resistor, we'll call this R sub E, right? It has some value R sub E. So you have this voltage potential, you have current that's moving, driven by this potential, but the amount of current is really governed by the magnitude of the resistor. The larger, the more resistive, the more impedance that resistor has, the less current that's going to flow from high to low. So you'd write the current equation as I is equal to VH minus VL over RE. Okay, exactly the same concept applies to heat. So you can, without being really very wrong at all, say I have some hot temperature and some cold temperature and a thermal resistance, which we'll call R, and then you're going to get heat flow from the hot to the cold, which we call Q dot. Right? And of course, we're all familiar with the equation. Then it's Q dot is equal to Th minus Tc over R. All right, so the idea of the thermal resistance comes into play in that if you can find an equation that kind of looks like this, right? This difference of a potential of temperatures and then some things multiplying it, some constants multiplying it. Doesn't matter if they're numerator or denominator. We can call that 1 over R. And that becomes our thermal resistance. So in this problem here, we have that, right? We have Th minus Tc. We have a bunch of constants multiplying that. And so this can become 1 over R. So we'll say that for this problem, or I'll just right here, this stuff over here is basically 1 over R. Right? And we had called this R cylindrical in Maple. All right, so we'll use this idea of thermal resistance in a lot of ways. There are some limitations on it, though. So thermal resistance is only valid when there is no generation, and the problem is at steady state. Right, and think about why that is. We just went through that whole derivation to get to this equation. And the assumptions that went into that derivation were those things: no generation, steady state. If you start adding generation or steady state, this result doesn't apply anymore. Right? This result is wrong for that situation. Okay, so let's see where we're going with this. Let's look at the resistance formula for the different geometries that you might encounter. This is obviously in a textbook, and you can get the table from the lecture notes later. But we went through and did this one here, cylindrical. So we know how this was derived. It was derived by enforcing the temperature boundary conditions. If you do the same thing, enforce temperature boundary conditions for a plane wall geometry or a spherical geometry, a spherical shell geometry, right? You will get these results respectively. So you can just look at this. I think the important things to point out are for the plane wall resistance, we're always worried about this. What is this value up here? This L. L is always the distance that you have to conduct, right? So if you have a plane wall, let's see if I can draw this up here, right? Let's say we have some plain wall and it's adiabatic, and we have temperature hot here, temperature cold here. So heat is flowing in this direction. The L that we're talking about is always the distance to conduct. It's the thickness of the thing that is between the two temperatures. And so this, let's see this here. This distance is L. Right? It's not the height. The other thing that we worry about is what is this AC? Right? AC is going to be this cross-sectional area. It's the area that's available to conduct. So the larger AC, the less thermal resistance there is. Right? There's more area available for heat to flow. Okay. Let's go through really quickly. Let's see, we have 7 minutes left. So let's go through the specific examples of the resistances. Again, this is hopefully review for you guys, but let's get through it. All right, so we've talked about the conduction resistance. There are the other mechanisms of heat transfer. You can represent those with resistances as well. Here we have some body that's at some temperature Ts. The surface is at temperature Ts. We have fluid moving over that. So we have a situation of convection. So convection. And convection is going to be modeled using, there's actually a name for this. It's called Newton's law of cooling. Not sure who this Newton guy is, but Q dot convection is equal to H bar times AS times Ts minus T infinity. All right, that's Newton's law of cooling. We can, all we're looking for again is a temperature potential and then some constants multiplying that to get us a resistance. So the resistance for convection is going to be 1 over H bar AS. AS, again, maybe it's obvious, that's the entire surface area that's exposed to convection. And T infinity is just the surrounding temperature. Okay, let's see. Radiation, you can do this something similar. I'm not aware of a fancy name for the radiation resistance equation. But let's write out the rate equation here. So that's Q dot radiation is equal to the surface area times sigma epsilon Ts to the fourth minus T surroundings to the fourth, or T infinity to the fourth, whatever you want to call it. All right, this one is maybe a little bit tougher because, let's see, we have Ts to the fourth minus T surroundings to the fourth as opposed to Ts minus T surroundings. So we have to maybe play some games with this, right? Oh, by the way, epsilon is the surface emissivity. And sigma is the Stefan Boltzmann constant. Stefan Boltzmann. And that is 5.67 times 10 to the minus 8th. That's the easiest constant you'll ever come across. What is it? Watts per meter, Kelvin to the fourth are the units on that. Okay, so, and then AS is the same surface area. So we need to figure out how to get this to actually look like a resistance formula because T to the fourth is not it. So it turns out, we can factor out the T to the fourth, and that becomes equivalently written as AS sigma epsilon Ts squared plus T surroundings squared times Ts plus T surroundings times Ts minus T surroundings. Okay, so this looks a little bit better, except we've still got some things that we're trying to compute, like we don't know necessarily the surface temperature. Maybe that's what we're trying to compute as part of this problem. But we do have this driving potential, some other stuff, and then some constants. It turns out for radiation problems, most of the time, you can do a pretty good job of approximating this term here by using the product 4 times T bar cubed, where T bar is just the average of TS and T surroundings. All right, so I won't go through the proof of that, but you take my word for it. Okay, so what we end up with is AS sigma epsilon 4 T bar cubed TS minus T surroundings. Okay, and then this stuff out here becomes our 1 over resistance for radiation. All right? So as long as you, maybe you know T surroundings, right? You're at 300 Kelvin, and you know TS is in the ballpark of 330 or something. You can kind of anticipate what that product is going to be, and it's not actually a really strong function of any of the individual temperatures. Right? So this is an approximation. You're using an approximation to get you this 1 over R rad, and you can update that. Maybe you do the calculation, you find TS is different. You can update your T bar value, right? But in the end, it's an approximation that helps you better understand the problem. Okay, let's see. So I think I might have time here to go through the last example. Let's see. Yeah, so let's think a little bit about how to use the resistance idea and maybe sketch out temperature profiles just from understanding resistances. Okay, so we have here this example of two materials together. Material A is high conductivity. Material B is low conductivity. So right there's a K sub A and there's a K sub B. And without even doing calculations or knowing specific values for this, we can sit here and look at this and decide roughly what the temperature profile is going to look like in this body. All right, so let's sketch out temperature as a function of position here. I'm going to bring down my little divider. So temperature as a function of position x, and over here we are at what, 2 times L. This is at L, and this is at 0. So if I know to start that I'm going to be holding this surface over here at TH, I'm going to be holding this surface over here, say this is at TC, I immediately can have some estimate of what the temperature distribution is going to look like. First of all, this is a plane wall. Right? So in a plane wall, the temperature profiles are linear if it's at steady state. So the question is, I want to pick the temperature, at which these things are going to intersect. Right? At the interface, there has to be a common temperature here. So would I pick this value, or this value? Remembering that Ka is higher than Kb. Yeah, why is the top one?
Less temperature drop.
Yes, exactly. Right? Oops, sorry. So it's going to look something like this. Right? I know that the conductivity is higher, so I know the temperature drop has to be lower. Right? And you can go back and you can look at the thermal resistance formula. You should see that for a higher conductivity, you have a lower thermal resistance. Right? So it all should make sense there. OK, I'm past time. We'll leave it there and continue next time. Thanks, everyone.